With Ethernet, each packet is a burst of high and low voltages which represent the ones and zeros of binary encoded data, and these packets are broadcast on the LAN. Every machine sees the packets, but only the recipients choose not to ignore them. But there's a limit to the length of the backbone. About 100 meters is the maximum with regular copper cable. Electrical signals get weaker on long stretches of cable. The technical term for this is attenuation. A device called a repeater can be used as a simple amplifier to boost the signal. Not only that, but we now have a segmented network. Segmenting a network not only allows us to build larger LANs with longer stretches of cable, segmentation can also reduce the amount of network traffic and make the network more efficient. This can be achieved by using the appropriate connecting devices. Let's take a closer look at repeaters, switches, and routers. Here's a segmented LAN with 5 different segments. Segment 1, Segment 2, 3, 4, and 5. And these segments are connected together by 2 repeaters, repeater A and repeater B. We have a sending computer and a recipient. When the sender broadcasts a packet, repeater A retransmits the packet onto 2 of the segments, and repeater B retransmits the packet on the other 2 segments. In no time at all, the packet has been propagated across the entire LAN. This means the recipient will get the message all right, but there'll be an awful lot of unnecessary traffic elsewhere. So, as you've seen so far, a repeater is nothing more than a simple amplifier that will boost signals on a segmented LAN. But it does nothing to reduce the unnecessary traffic. In fact, it generates more. Imagine a very badly designed LAN with a circuit of repeaters like this. Each will end up retransmitting its own signals over and over, resulting in what's known as a broadcast storm. A big LAN with lots of segments is more likely to use switches instead of repeaters. Here's the same LAN again, but this time it's using switches. A switch will amplify signals just like a repeater, but it can also reduce the total amount of traffic on the network. How? Because a switch knows the MAC address of every computer on every segment connected directly to itself. It also knows which segments those machines are on. Let's give each segment a number. Switch A knows the MAC addresses of all the computers on segments 1, 2 and 3, because these segments are connected directly to itself. Switch A also knows which segment each of these computers is on. Switch B knows the MAC addresses of all the computers on segments 1, 4 and 5, because these segments are connected directly to itself. Switch B also knows where the computers are. When the sender broadcasts a packet, switch A rebroadcasts it onto segments 2 and 3 because it doesn't know anything about the recipient. Switch A is behaving like a repeater. Meanwhile, switch B knows the recipient's MAC address and it knows it's on segment 4. So switch B will only propagate the packet onto segment 4. You can see then that one of these switches has filtered the traffic. You can probably imagine on a large LAN with a lot more segments, there's potential for a lot more filtering. Indeed, if the sender and recipient were on the same segment, then their packet broadcasts would be restricted to that particular segment. Let's recap. A switch knows the MAC address and segment location of every computer on every segment connected directly to itself. It stores this information in a table in its own memory. A switch can reduce the overall amount of broadcast traffic on the LAN, depending on where the senders and recipients are located. Broadcast storms are less likely on a switched LAN than if repeaters were being used, but they can still happen if the way the switches are connected together hasn't been thought through properly. A switch also does what a simple repeater does. It's a voltage amplifier. Here's the same LAN again, but this time with routers instead of switches. The key thing about a router is that it knows the MAC address of every single computer on the network. and it knows which segment every computer is on. When the sender broadcasts a packet, router A knows not to bother rebroadcasting it, so segments 2 and 3 remain quiet. Meanwhile, router B knows that the packet needs to be broadcast onto segment 4, so segment 5 remains quiet. This is the ultimate in packet filtering. Each router keeps the information it needs in a routing table, including information about the location of other routers. This means a router knows the quickest way to get a packet to where it's going on a big segmented LAN. Not only that, but routers talk to each other when devices are added or removed from the LAN, so they always have the most up-to-date information. So let's recap routers. A router maintains a table of MAC addresses and segment addresses of all the computers on the LAN, including information about other routers. On a routed network, packets are only broadcast where they need to be. They take the quickest route and there's no unnecessary broadcasting. Routers provide a high degree of traffic filtering. Broadcast storms are not possible on a routed LAN when it's working properly. Routers configure themselves. They share up-to-date information about what's on the network automatically.